So welcome everyone, I'm Norman Wildberger, and I'm going to talk today about three-dimensional geometry, Zome, and the elusive tetrahedron. So we're going to have a look at three-dimensional geometry from a somewhat new way, with the aim of trying to understand the metrical geometry of a tetrahedron. And we're going to use this lovely construction system, Zome, to illustrate quite a few things. So the plan of the talk is, don't worry, I'll use this one. The plan of the talk is to first introduce some basic ideas of affine and projective rational trigonometry. So we're going to change our point of view here. We're not going to use the standard approach to geometry. We're going to use this relatively new rational trigonometry, which I'm going to tell you about. So you don't need to know anything about it. Then we're going to introduce the Zome construction system, and we're going to list some primitive Zome triangles. We're going to discuss a particular Zome tetrahedron that comes naturally arising from the dodecahedron. And then the main part of the talk, we're going to develop some of the main laws of three-dimensional trigonometry, which is really the study of a general tetrahedron. We're going to illustrate these basic laws and give some projects and challenges for amateurs who would like to have some interesting projects to work on. So the history of the tetrahedron is a very long and illustrious one, going back to the ancient Greeks, one of the Platonic solids, and many prominent mathematicians have worked on the tetrahedron. The tetrahedron is a lot harder than a triangle. Okay? Understanding the geometry of a tetrahedron is a major task, and it's probably fair to say that it hasn't really been done in complete detail. The best paper that I know is more than 100 years old by G. Richardson, called The Trigonometry of the Tetrahedron, in the Math Gazette in 1902, which gives a relatively good study of the classical trigonometry of the tetrahedron, but it's not going to have very much at all to do with what we're going to present today, which is going to be a rational analog, but nevertheless the formulas that we introduce will be, a lot of them will be analogous to the ones here. Okay, so the basic object that we're working with is a tetrahedron. There's a picture of a tetrahedron, points P1, P2, P3, P4, and there's a more concrete three-dimensional example of it. And prominent for us will be the quadrances of the sides, and I'll explain what that is in a second. Traditionally, however, classical trigonometry deals with the various relations between the 6 side lengths, the 12 face angles. That is, every face, is a triangular face, has 3 angles in it. Whoop. Let's go back. So altogether, 12 angles in the various faces. Then there are 6 dihedral edge angles, which are very important. These are the angles created by adjacent faces. So if you take that face there and that face there, then those 2 faces make an angle. And that's called a dihedral angle. And of course, then there's the 4 solid angles. At each vertex, there's something called a solid angle. And then there's the volume of the tetrahedron itself. There are also secondary quantities that we're not going to worry about. And it's probably fair to say that this has nowhere been done completely in terms of understanding all the relationships between these various things. And our approach is that we're going to use rational trigonometry, and we're going to start with the quadrances Qij. So that's in vector notation. It's very simple. The quadrants between 2 points is the dot product of the vector joining them with itself. Okay? So we're going to use some basic elementary linear algebra to introduce the main concepts and the main formulas. Okay, so here is our strategy. We're going to look at this tetrahedron in 2 different ways. We're going to combine 2 different geometries. We're going to combine a planar point of view and a projective point of view. So the planar point of view comes about when we just look at a face. One face of the tetrahedron is an ordinary triangle, so obviously we need to understand a triangle. That's what I call affine rational trigonometry. But there's also something else. There's also what happens at a vertex. At a vertex, we have 3 lines coming out, and that forms what could be called a projective triangle. And we're going to need a variant of rational trigonometry called projective rational trigonometry to deal with those 3 lines emanating from a vertex. And then what we're going to do is we're going to combine these 2 different trigonometries to put them together to study the solid tetrahedron. Oh, wrong direction again. Okay, so let's start with the basic definitions using only first year linear algebra. So the main object is a vector space or a linear space and a dot product or an inner product on it. For the mathematicians, symmetric bilinear form over a vector space. And here's the familiar one that you can think about, just the ordinary dot product in two-dimensional space, or perhaps in three-dimensional space, one dimension up. And the main definition that the quadrants of a vector is just what you get when you dot the vector with itself. And then we say that the quadrants between points is the quadrants of the vector joining them. Here's our notation for quadrants to distinguish it from distance. And here's an explicit formula for the quadrants between 2 points, just the difference between the x-coordinates squared plus the difference of the y-coordinates squared. And it's crucial that there's no square roots around. This is a purely algebraic quantity, making it much easier to work with than the distance. I'll keep doing that now. Okay, so now the real innovation in rational trigonometry is when we go to angles and replace them with a new concept called spread. So you're all going to have to take a big breath and absorb this crucial definition. Okay, what is the spread between two lines? Well, here it is. So given vectors v and w, here is the definition of the spread between the vectors v and w. It is 1 minus v dot w squared, that's the dot product between v and w, divided by the quadrants of v times the quadrants of w. So the quadrants of v is just v dot v, so we can rewrite it purely in terms of the dot product this way. And this will be a familiar kind of thing. You will all know that if you remove the 1 minus and just look at this quantity here, and you take the square root of that, and then you take an arc cosine involving some rather complicated transcendental function, then you get the usual notion of an angle. So here we're doing something much simpler, much more elementary. We're dispensing with the square root. We're dispensing with the arc cosine. We don't even need to know what that means. We don't need a calculator. We're going to stick with just this expression. This turns out to give us a huge amount of power. Okay, this turns out to be the right thing to do. Okay, so let's have another look at it in terms of coordinates. So if we have two vectors, x1, y1, x2, y2, here's the dot product, here's the quadrants. There's a remarkable identity that helps us here to perhaps rewrite this, going back to Fibonacci, in fact even to Diophantus, that allows us to rewrite this expression in this form. And in this form, we have another interpretation of what it is that we're doing when we're looking at a spread. So here's two vectors. Okay. So what we're doing when we form the spread between these two vectors is we're looking at the numerator is a determinant. You can think of that as an area of the parallelogram formed by those two. We're squaring that area. And then we're normalizing by the squared lengths, if you like, of the sides. So it's a square determinant, suitably normalized, so it doesn't actually depend on the vectors, but only depends on the lines. Okay, in online you can have a look for a spread protractor. The spread between the two lines goes from 0 to 1, and it's not exactly linear. Then it would be angles, but it's not too far from linear, except near a 0 and 1, where it's the quadratic aspect of it becomes clearer. And it's also important to realize that the spread is between lines and not rays. Very important. Okay? Angles are naturally defined between rays, spread between lines. Okay, so now we come to trigonometry. So here are the three main laws of rational trigonometry concerning a triangle and three quadrants, Q1, Q2, Q3, and three spreads, S1, S2, and S3. What are the relationships between these 6 quantities? Here they are right here. The first one is the cross law. It's the most important law. It's one of the most important laws in mathematics. Okay, Q1 plus Q2 minus Q3 squared equals 4Q1, Q2, 1 minus S3. The second one is the spread law, which says that the ratio of S1 to Q1 equals S2 over Q2 equals S3 over Q3. And the third one, the triple spread formula, gives us a relationship between the three spreads. So these are obvious analogs of the cosine law in classical trigonometry, of the sine law in classical trigonometry, and of the fact that the three angles sum up to 180 or, what is it? Pi. Okay, this cross law turns out to be the most important one. It allows us, for example, to calculate a spread if we know the three quadrances. And if we know two quadrances and a spread, we can get a quadratic equation for the other ones. Okay, I'm going to prove these laws to you now, assuming you have never studied trigonometry and you've only taken a first-year course in linear algebra. I have to go the right way, though. Okay, so here is the proof of the cross law on this page. Okay, only using first-year linear algebra. Basically just the properties of the dot product. Here's our triangle. And let's have a look at this quadrant's Q3. By definition, that's the quadrants of the vector A1, A2. We write that vector A1, A2 as the difference between the vector A3, A2 and A3, A1. So it's that vector dotted with itself. Okay, by the bilinearity of that dot product, this one dotted with this one is the quadrants between A3 and A2. That's what we call Q1. The plus this one here, whoa. Go back. This one dotted with this one is the quadrants Q2. And then we have twice, minus 2 times, the dot product between A3, A2 and A3, A1. It's a symmetric bilinear form, so the two things combine. So that's just a relation. Let's keep that in mind. And now let's go back to the definition of the spread, S3. What was this spread? It was 1 minus the dot product between this vector and this vector, all squared, divided by this quadrant times this quadrant. Well, we've just established a formula for this dot product. Here it is right here. Okay, so we're going to replace this dot product using the previous formula. The previous formula tells us that we can replace it with Q1 plus Q2 minus Q3 divided by 2. So we put that in there and square it, and we get that formula there. And we clear denominators. We get the cross law. So that's one of the most important formulas in mathematics and in geometry. And we've proven it, I think you all have to agree, in a very elementary way, without any transcendental functions or waffling about angles. Okay, next law is the spread law. We're going to prove it now. Here's the proof of the spread law, the second main law. Here's the cross law that we've just established. We rewrite it this way by bringing the 4Q1, Q2, S3 to one side. And what we have left, we rewrite it just by using a bit of algebra, so it turns out it's in symmetrical form. We call this important quantity the quadria of the triangle, and we denote it by A. It turns out that but we don't need this, that this is the 16 times the square of the area of the triangle. That's essentially Heron's formula, a rational form of Heron's formula, that statement. But we don't need that, but just to orient you what that is. Okay, now the beautiful thing is that this quantity here is symmetrical between Q1, Q2, and Q3. So although we computed it this way, we could have also computed it this way, and so these three things must all be the same. And so when we divide this formula by 4 Q1, Q2, Q3, we get S1 over Q1 equals S2 over Q2 equals S3 over Q3 equals A over 4 Q1, Q2, Q3 as a bonus. So that's the spread law, or the analog of the sine law. Oh, I have to figure out how to go forward. Okay. And our third main law, the triple spread formula. How are we going to prove that? We're going to combine the cross law and the spread law. There's the spread law that we just proved. We're going to set this common ratio equal to 1 over d. We don't care what 1 over d is, but whatever it is, it then tells us that Q1 is equal to ds1, Q2 equals ds2, and Q3 equals ds3. We're going to substitute that into the cross law. Here's the cross law yet again. I'm going to replace the q's with these expressions. So then there's a common d here that pulls out as a d squared, and we have s1 plus s2 minus s3, all squared. Here in Q1, Q2, we have a common d squared that pulls out, and the s1, s2 left. When we cancel the d squareds, we get a relationship between the three spreads. When we unwrap that, we get the triple spread formula. All right, so that was trigonometry, what, in 10, 15 minutes. Okay? Not 3 years, well, or maybe 2 years, or maybe 6 months, but certainly most high school students do not learn trigonometry in an hour. But they possibly could. They possibly could. This is all just high school stuff. Okay. Now we're going to move to something a little bit more complicated. We're going to look to the projective analog of this thing. So I'm going to have to just involve a little bit of projective geometry. So for us, projective geometry is not about an ordinary triangle, but about a projective triangle. So here's a projective triangle. Okay. What is it? It's 3 lines emanating from a common point. Okay. And that's a picture of it right there. So we can think of this point, if we like, as the center of a sphere. And then these 3 lines are coming out and meeting the sphere in various points. And the 3 planes formed by those 3 lines meet the sphere in these great circles. Okay, so with coordinates, well, a projective point can be interpreted in terms of a triple. A plane can be written in linear algebra form as a Lx plus My plus Nz, so it's essentially given by a triple, homogeneous triple of coordinates. And then we can write down expressions for the spread between these two lines. So the crucial thing is we have lines in space. If we just look at 2 of them, say the yellow one, or the yellow one and the blue one, those 2 lines have a spread. We've just talked about spread. So we can define the quadrants between these two projective points as being the spread between the 2 lines that they actually are. On the other hand, if we take 2 planes, which are essentially the projective lines, these great circles, then we can take those 2 planes and they're both determined by normal vectors. So if we take the angle or the spread between the 2 normal vectors, we can associate that as the relationship between the 2 lines. So it all comes down to spreads. We're either taking the spread between 2 lines or the spread between 2 planes to determine the 2 fundamental concepts in projective rational trigonometry. And so here's our notation. The notation is kind of opposite to the planar one, so I'm going to use small a1, a2 for points and capital L's for lines. So the 3 points now are the points a1, a2, a3, which we're actually going to visualize actually just as points. And the 3 lines are the planes determined by them. In other words, what we'd like to do is we'd like to think 2-dimensionally, even though it's actually a 3-dimensional picture. So we imagine these 3 lines that we're considering emanating from the center of the sphere and meeting, say, a sphere at these 3 points here. And then the spherical triangle that we're considering, the projective triangle, we can visualize it this way. Okay. So the notion of spread gives us a notion of 3 projective quadrances and 3 projective spreads. And then there's projective analogs of the rational trigonometry relations, and here they are. And these are basically equivalent to the formulas for spherical trigonometry. So if you've ever looked at astronomy books, they're full of formulas in spherical trigonometry. These are the essence of those formulas. So the projective spread law is exactly the same as the planar one. The cross law is a bit more complicated, but still a very beautiful formula. It's a quadratic equation that tells us how to calculate one of the 3 spreads if we know the 3 projective quadrances. And there's a dual formula which is exactly the same except that the quadrances and the spreads are reversed, which looks like that. And it would take me more time to prove those things. So I'm not going to do that. But we're going to use those laws in an important way. I want to mention one more quantity that's important for the projective triangle, which is the analog of the quadria. Remember that was 16 times the area squared? Well, there's a projective analog of that, which we'll call the projective quadria. I'll call it S. And we can define it by this formula, which is sort of analogous to the planar version, or perhaps like this. So it's what you get when you take this spread and you multiply by the two adjacent quadrances. And it doesn't matter which place we do that at. There's another interpretation which I want to point out, because this notion of spread is going to be important for us. This notion of, it's going to give us the notion of solid spread. So if we just look at this tetrahedron here, we consider these three lines emanating from this point, then the projective quadria of this projective triangle that's sitting here can be thought of in this way. We can lay down the tetrahedron so it's flat on the ground, okay? And then we can measure that base spread. That's a spread. And then we still have this one going up. And then we can measure how high up it goes. In other words, we can measure the spread between this one and the base plane. You know, so you might call it pitch. My friend Max Wilson says we should call this pitch, which is maybe a good idea. So it turns out that this projective quadrant is just the product of this base spread times the pitch. And that's independent of which side you lay down on the ground. Okay, so that was rational trigonometry, both in the planar and in the projective setting. So we have a lot of power with those formulas, although you may not appreciate it at this point. Now let's look at Zome construction system, which is a remarkable innovation created by Steve Baer and his wife Holly in 1992, and with design work done by Marc Pelletier and Paul Hildebrandt. Okay, so the idea is that we have struts of 3 different colors, the blue, red, and yellow, and 3 different sizes. Each one of them come in 3 different sizes, and they fit into these white balls that you've seen with 62 holes. And this system is very flexible. It allows us to construct the Platonic solids and many even 3-dimensional models of 4-dimensional polytopes, like the 120 cell and the 600 cell. So where do these 62 holes come from? Okay, let me explain that. So here's a dodecahedron, which I hope you have all seen. Okay. Now if we look at, we're all looking at this central fellow here. There are 10 lines going through the vertices of the tetrahedron. There are 10 yellow lines, because there are 20 vertices, and 20 divided by 2 is 10. If we looked at the centers of the faces, I haven't built it here, but we would get an icosahedron. It has 12 vertices, and so there are 6 lines going through its vertices. So 10 lines for the dodecahedron vertices, 6 for the icosahedron vertices, and then there are these 30 edges that both objects have, and if we draw a line right through the middle of every edge with its opposite, we get 15 new lines. So 6 plus, what did I say, 6 plus 10 plus 15 makes 31 times 2, because there's a hole on either side. That gives us the 62 holes in this system. Okay, so one of the things that one can do is, first one wants to analyze this. If you want to analyze this thing using classical trigonometry, you will find it a big challenge. Okay, and that's why it hasn't really been done so effectively. But with rational trigonometry, everything is a breeze. Okay, so the key, and it's a great exercise to do. If you have a Zome system at home, you can work this all out. Okay, it's a couple of days of a lot of fun work. So what we're going to do is we're going to figure out the relationships between all the struts and all the spreads that we can possibly make. So first we build a pentagon, and we can build 2 right triangles, and so just by staring at those, we can figure out, and if we know the relations in a pentagon, we can figure out that we can normalize the quadrances of the 3 blue struts so that the smallest one is, say, 1, and the next one is tau, and the next one is tau squared. What is tau? Tau is 3 plus root 5 on 2, which is the square of 1 plus root 5 on 2. That's a square of a golden ratio. Okay, so that's in fact the ratio of any one of the colored struts to the next one up. So it turns out that if the blue one has quadrants 1, then the red one has quadrants beta, and the yellow one has quadrants 3/4. What is beta? Beta is 5 plus root 5 on 8. It's an important number in rational trigonometry. So those are the sizes or the quadrances of the smallest ones. The next ones up are all multiplied by tau. The next ones up are all multiplied by tau. Okay, here is a pentagon, a regular pentagon, and here are the spreads that figure in a regular pentagon. These are zeros of the fifth spread polynomial. Anyway, these are the values. They're alpha and beta, 5 minus root 5 on 8, and 5 plus root 5 on 8. They play the role of 36 degrees and 144 for this one, and this one plays the role of 72 degrees and 108. Okay, once we've done that, we can construct with Zome an equilateral triangle that you can easily do with the blue struts. Do I have an equilateral triangle around? Yes, you can see one here. So there's a blue equilateral triangle. And you can construct this triangle and this triangle. So here this one is 1 and this one is tau. This is the smallest one and these are the medium blues. And these spreads here will be betas, and that spread is alpha. This is called sharp, and this one is called flat. And these triangles figure prominently in the theory of Penrose tilings. So we can construct them very nicely. And then we can construct, well, then we can ask, well, what triangles can we make with Zome? And what do they look like metrically? So here is my list of two-colored primitive Zome triangles. These, when I say primitive, I mean that I'm only using a single strut for every side. There are a few more if we allow double struts. Okay, but these are the sort of the primitive ones. And I've shown you what all the quadrances and more interestingly, the spreads are. Okay. So for example, this spread is 4/9. This spread is 16 beta over 15. That's 16 alpha over 15. That one's 8/9. That one's 2/3. These are natural numbers that are intimately connected with the Zome geometry. If you wanted to calculate angles, you would just get the usual random 5.496345 ... kind of stuff. Okay. This is the real story. Okay, then there are three-colored primitive Zome triangles which have, well, three colors. And here they are. And it's fun verifying that. Calculating what all these spreads are using the laws of rational trigonometry. It's an excellent exercise.
What's T-bar?
Oh, T-bar, yes, I didn't say. Tau was 3 plus root 5 on 2. The tau bar was 3 minus root 5 on 2. That's a very small one there. Okay, so now we can get to a tetrahedron. We're now going to go to 3 dimensions. And we're going to consider one particular tetrahedron that figures prominently in the dodecahedron, just sort of to focus our minds. Okay, so there's a dodecahedron, and here is the line coming out. That's the center of the face. That would be one vertex of the associated icosahedron. And I'm going to join this thing up with these two things here, and I'm going to take this, and the center, and I'm going to pull that tetrahedron out. Okay, and it looks like, there it is there. Good stuff, pull that out. So that's a particular tetrahedron that we can make with Zome, and we can, say, study it. Okay, so one thing that we know all the Zome triangles, so we know all these 4 triangles. They're in our list. So we can immediately write down what all the quadrances are. I've done that here. Those are the boxes. And we can write down what the spreads of the faces are. So, for example, the spread between the 2 yellow ones is 4/9. Okay. And so on. Okay, so we want to study the tetrahedron now. Okay, and we'll keep this one in mind. At the end of the day, we want to understand this tetrahedron, let's say. Okay, so what do we know about the trigonometry of the tetrahedron? Well, probably the most important formula goes back to Tartaglia. Tartaglia is famous for his solution of the cubic equation, but he should equally be famous for this formula here. It's a formula for the volume of a tetrahedron as a function of its side lengths. Actually, better, the side quadrances. The 6 quadrances determine the volume of the tetrahedron by this formula, that the volume squared is 1 over 288 times this determinant. And if you expand that determinant out and you multiply it by 144, then the coefficients are nicer. They're all plus or minus 1, and here they are right here. How can you remember this formula? Well, this is actually easy to remember if you do the following trick. You make a 3 by 3 matrix which has its vectors, say the 3 vectors emanating from P1. Call those vectors V1, V2, and V3, and you make a matrix. And then you multiply that matrix by its transpose. This is a great thing to do in mathematics. You have a matrix multiplied by its transpose. Then the various entries are the dot products between the vectors and themselves. Okay? And these are just the expressions for those dot products when you rewrite those dot products in terms of quadrances. So the proof of this is not hard at all if you know a little bit of linear algebra and determinants. Okay, so the first other relation I want to point out is the alternate spreads theorem, which it's probably easier if I just state it using an example. So we're just sticking with the spreads on the faces. If I choose one point, then these 3 triangles that are emanating from this one point have 2 spreads here, and 2 spreads here, and 2 spreads here. So this theorem is that if I take the ratio of these 2 spreads and multiply by the ratio of these 2 spreads and multiply the ratio of these 2 spreads, then I get 1. That's an elementary consequence of the spread law if you think about it for a few minutes. Of course, in every triangle face, the 3 spreads must satisfy the triple spread formula. The analog of the 180 sum of angles is 180 degrees. So of the 12 spreads faces that we have 4 such triple spread formulas and 4 such alternate spreads theorems. But it turns out that these 4 are not independent, that if you multiply them all together, you get 1 equals 1. So there's a relationship between these 4 alternate spread relations. So altogether, there's really only 4 plus 3, that's 7 independent relations on these 12 things. And there is ultimately 5 degrees of freedom. If you know 5 of the 12, you can, in theory, calculate the other ones.
Sorry, I'm a little bit lost.
Yes?
Why doesn't S24 equal S42?
Okay, well, what's my notation? I didn't say that yet. My notation for the spread, so what does this spread S21 mean? It's my notation for the spread which is on the face at the vertex 2. In the triangle 1, in the triangle 1, this is the triangle 1 which is opposite the vertex 1. So the notation for the spreads is not quite symmetric. Thanks. Okay, so that's a relatively benign thing. So now we come to sort of essentially the heart of the matter. So the heart of the matter is that the tetrahedron also has face spreads or dihedral spreads. Okay, so we're going to denote those by Eij. So for example, E14 E14 is the spread between the 2 faces that meet along this edge Q14. Okay, along that edge there are 2 faces that meet, and they have a spread. They form some spread. And that's a dihedral spread, which we're going to call E14. Now if we look at this tetrahedron from the point of view of P1, those 3 lines emanating out, we get a projective triangle whose spreads are E1, E2, and E12, E13, and E14. The spreads between the faces determined by those 3 lines emanating from P1. And whose projective quadrances are the face spreads between those 3 lines emanating from P1. So in other words, the 3 spreads, the face spreads S1, S4, S14, S12, S13 form essentially the quadrances of this projective triangle, and the 3 edge dihedral spreads E12, E13, and E14 form the sort of the spreads of that. But we know that those must satisfy the cross law. This is the cross law in the projective rational trigonometry. One of those two big formulas that we wrote down at the end of that thing. So it's a quadratic equation involving the E12, let us say, and all three of these spreads. Okay, now what we're going to do is we're going to combine this projective cross law with the affine cross law. We can do that because we have a tetrahedron. So to come back here, so here's one of the spreads Sij, say S12. Okay, this spread here is part of this triangle. And so we can write it down from the planar cross law in terms of these three quadrances. Okay, that's what I'm doing here. So on the right-hand side, this 1 minus S12 is exactly this expression here, which maybe is familiar from the planar cross law. And the beauty of it is that once you write down these three things and stare at it, you see that the right-hand side becomes a perfect square. So what started out as a quadratic equation is really no longer a quadratic equation. It's a product of two linear equations because it's saying this squared equals this squared. It means it factors as two linear equations. And you can almost write down the value of E12. Almost, but not quite, because there are these two linear equations that you have to choose from. Well, now we're aided by another pleasant aspect, is that, say, this edge Q12 and the edge dihedral spread that we have there figures not just at that vertex, it also figures at that vertex too. In other words, there's another projective cross law at this vertex, which gives us also a quadratic equation for E12, which also factors into two linear factors. So now we have these two different expressions, and we can easily just pick out what the common solution is, and we can write down E1, E2 as a purely irrational combination of the quadrances. Because this is a major formula now. So once we've unraveled this, we replace all the Sij's with the corresponding expressions in the quadrances. We get a formula for, say, the edge E12. And it's a big formula. It's a big formula because it contains in the numerator the quantity V. What was V? That was 144 times the volume squared. That was that big expression involving those many terms involving the QI's at the bottom of one of the sheets. And what are the denominators? Well, the denominators are the quadrias of the corresponding faces. Okay, so let me express this formula in terms of our tetrahedron here. If this happens to be the vertex 1 and this is the vertex 2 and here's the edge E12, then if we want to find this spread, what we do is we take 4 times the quadrants Q12 multiplied by this quadroom V, divide by the quadria of this face times the product of the quadria with this face. So these two faces which meet here, they provide the denominators to this expression. So that's a calculation from the previous slide, admittedly with a computer. All right, well, by symmetry, it's symmetrical. We can solve for V, so we get a formula V equals E12.
Sorry, what did you mean, admittedly with a computer?
Well, it's a big formula. So you want to employ some software, some algebraic software to help you factor and so on and so forth. Although in principle you could do it by hand. So here we've solved for V in terms of E12, and the whole thing is symmetric because this is essentially the volume squared. So we have actually 6 such formulas, one for every edge, dihedral edge spread. And we can do some pleasant things with these formulas. For example, we can divide, we can multiply this one times this one, and then divide out, and we get that the ratio of E1, E2, E1 to E34 to Q1 to Q34 is constant. What does that mean? So every edge has an opposite edge. This edge is opposite to this one. So what I'm saying is that if you calculate that edge spread and divide it by this quadrants, and then calculate this edge spread and divide it by its quadrants, that quantity is independent, only depends on the tetrahedron. It doesn't depend on the choice of two edges that you took. If you take another pair of opposite edges, you get the same number. What you get, in fact, is 16 times the quadroon squared divided by the product of the quadrias of the four faces. So you may recall that when we were talking about projective triangles, I also mentioned this projective notion of quadria, and I called it S. And it had a formula like this. Well, since we have a formula for E12, we can now prove this solid spread theorem, that S1 is the quadroon divided by 4 times the product of the quadrants as emanating from that vertex. And here's the proof. Basically 2 lines. There's the formula. There's the formula for E12 that we just derived. Then we write out the quadrias of the bases, of the denominators. We do some calculation, cancellation, and we get this formula. So what this is telling us is another interpretation of what the solid spread is. Okay? The solid spread can be thought of as the V, which is essentially a determinant, divided by the product of these quadrances. So this is some kind of three-dimensional analog of that relation that I said about with a spread. The spread can be thought of as a ratio of a determinant squared, divided by 2 adjacent quadrias. Here, it's a determinant of these 3 things, suitably divided, normalized by the adjacent quadrances of the sides. And we get some additional pleasant formulas. And we get, as a consequence, a three-dimensional analog of the spread law, or the sine law, which says that if you take this solid spread and divide it by the product of these 3 quadrances, the product of the 3 opposite quadrances, then that's independent of the vertex you chose. So this equals this equals this equals this, and this is sort of what you can write down what the right-hand side is. It's a three-dimensional analog of the spread law, showing that this notion of solid spread really deserves to be the kind of right notion. People who are trained in classical trigonometry will say, no, we should use the spherical area. We should use the solid angle. Okay, solid angle is obtained by cutting it with a sphere and taking a spherical triangle and taking an angle defect and so on. Okay, this is different. This is different, and I think the algebra suggests that it's a very viable alternative. Okay, there's some more formulas. Here's a few special cases. If you have a tetrahedron with a fully right vertex, then first of all, the quadria of the face is the sum of the 3 quadrias. And secondly, the 3 solid spreads at S2, S3, and S4 satisfy this relation. In general, the 4 solid spreads don't form a relation, but here in this special case they do. Okay, now a little bit more complicated. Here's we're kind of meeting some more serious algebra here. So a question is, what is the relationship between these 6 dihedral spreads? It turns out that the 6 dihedral spreads are related by an algebraic equation. But it's not entirely trivial to write it down. Okay, so here I've written it down. Okay, so you have to introduce these intermediate quantities, and then you have to introduce, well, you don't have to. This is the way I happen to get it, but it's not necessarily at all the best way, okay, but it's the only way I know. Then you introduce this quantity, and you introduce this quantity, and then this turns out to be the relation. If I actually wrote that down explicitly in terms of E1s, E2s, and so on, it would probably take dozens of pages, maybe hundreds of pages to write the whole thing down. But nevertheless, if we actually look at a specific example, so if I make up 6 quadrances, which we can do because we can basically choose any 6 quadrances to form a tetrahedron, and look at the formula that we've established, that'll establish the edge spreads, then you can ask the following question. Suppose you rubbed out E12 and you didn't know it. How could you find out what it was? Well, that previous formula, if you go through the motions, you'd find a polynomial relation for E12. It's this thing here. It's of degree 8. And it conveniently factors into 2 linear factors and mysteriously into 3 quadratic factors. One of these linear factors is the tetrahedron that we've got. The others presumably are somehow linked or closely associated tetrahedron. And I confess to not understanding that at all, what's going on there, or why this takes this particular form. What's the meaning of these quadratic equations? Okay, so let's return to our tetrahedron that we had a look at to begin with, that one there. We're now in a position to use those formulas to write down so we can see what these things look like. What do we actually get? Well, here are the various quadrances. We wrote those down before. The quadroom, 144 times the volume squared, is 9 over 4 plus root 5. Here are the quadrias of the faces. Immediately, that was a surprise to me because it's obvious that this face has the same area as this face. It's not at all obvious to me that this face has the same area as this face. Is that obvious? Not at all, right? This face here is the same as that area. That's what this is telling us. I suspect that a lot of pleasant surprises like this await anyone who takes an in-depth study of these Zome things. Okay, then I've calculated the various edge dihedral spreads. There they are. 3 of them are beta, 2 of them are 3/4, 1 of them is 1. That one there is perpendicular. And the 4 solid spreads, there they are there. These 2 are obviously the same. Let me connect to just one classical formula from, well, not antiquity, but from 1821, due to the famous mathematician Krell, very prominent German mathematician who created Krell's journal, which is a very famous journal in the 19th century. And he studied the tetrahedron, and this is a somewhat reformulation in rational trigonometry, but it's essentially his formula, saying that if you're interested in the sphere that goes around the 4 points, how big is that sphere? What is its diameter? It's a natural question. So this is not the diameter, this is the square of the diameter, okay, because we're working with quadrants. And the formula is that it's A star over V. V is the quadroom as before. And what is A star? A star is the quadria of the triangle that you get by taking opposite edges, the quadrances of opposite edges, and multiplying them. So you multiply those 2 quadrances, you multiply those 2 quadrances and those 2, you get 3 new numbers. You form a triangle with those 3 new numbers, and you calculate 16 times its area squared. That's that's the formula. And in our tetrahedron, you can work that out. It's 5 over 2. Okay, so now there's some challenges here, because this is not the only tetrahedron that one can make with Zome. In fact, Alejandra Place, who's John Place's daughter, sent me 65 pictures of the various Zome tetrahedron that one can make, which she made. Here's one of her pictures. So each one of these tetrahedron can be constructed and could conceivably be, well, not conceivably, can be studied metrically. In other words, one can calculate all the spreads and the quantities that I've been talking about. And that's a challenge that I think amateurs might be interested in. Right? So there's lots of things to do, calculations to be made. And I want to end sort of just very quickly with going back to something very much more simple. Here are the two most familiar triangles in ordinary planar geometry, the 90-45 triangle and the 90-60-30 triangle. Well, that's half of it. Okay. Here are these triangles in rational trigonometry. Side 1, 1, 2, spreads half, half. Here spreads 3/4, 3/4. Here the quadri is 3, and here the quadri is 4. Okay. These are the numbers that one really should learn instead of those root 3s on 2s and what is it, 1 over root 2s and things like that. Okay, so what are the analogs in 3 dimensions? The analog of the right triangle is this right isosceles tetrahedron. There it is there, and you can make it with Zome. But for that you need the green struts. Okay? The green struts are one level up from, haven't talked at all about them. That's sort of an innovation that allows you to make things like this. Okay. And anyway, here are the quadrias, the edge dihedral spreads. There's 2/3 there. The solid spreads 1 1/4. That's a solid spread of 1/4. And that's a Pythagorean example. And finally, going back to Archimedes and Plato, the humble regular tetrahedron, which you can make with Zome using the green struts. If we assume that each quadria is 1, then the quadrias of all the faces are 3. That's just an equilateral triangle. The quadroom is 2. It was 4 for the previous one. All the face spreads are 3/4, of course, and the edge spreads are all 8/9. That's an important angle for chemistry. It's the angle of a methane molecule, but done rationally. And the solid spreads are all 1/2. So although people have been studying these Platonic solids for a long time, this is perhaps the first time where metrically, it's actually, the metrical structure has been laid out like this, and it's relatively benign. Okay, so if you'd like to have some more information, there's my book on rational trigonometry. I have various articles on hyperbolic geometry, which doesn't seem to have much to do with this, but the formulas for hyperbolic geometry are exactly the same as the formulas for projective planar trigonometry that I've talked about. And then I have various YouTube videos, Wild Trig, Universal Hyperbolic Geometry, and a few others. So I hope some more people will help me investigate these things further, and it's an open door to more discoveries and constructions. Thank you.
Are there any questions or comments? Yes?
Well, first of all, a number of times we have sort of 1 minus s appearing, where s was your spread, as I understand.
Yes.
Doesn't that mean that there's a case for introducing co-spread
That's a very good question. Yeah, so the question is, the 1 minus s occurs quite a lot. So I do have a name for that. I call that the cross. That's why, and I call it C. And it was a subject of debate for me at the beginning whether I should use C or S as the fundamental thing. But it turns out that S is the right one. I'm pretty convinced now. And one of the reasons is the spread law, the analog of the sine law. That turns out to be a very, very interesting and powerful and pleasant thing that makes a lot of things simplify. So yes, it's an interesting thing. One should be aware that 1 minus s plays an important role.
Okay, and I guess second, I know that you were adverse to the use of square roots, but it seems that they sort of force themselves on you. And so you might as well sort of accept that.
Where I didn't see any square roots being forced upon us.
Root 5.
Oh, root 5s. Okay, the root 5, we just agree we're in an extension field. All right, so as far as I'm concerned, the root 5 here is not 1 point something or other. We're working in an extension field.
I'm not disturbed by that, but I mean, it does seem that you do need to use square roots from time to time.
Yes, from time to time, especially with practical applications, square roots.
Well, let me ask you actually about a practical application. Now, suppose that you're stuck in the desert and somebody, you have a mobile phone and somebody says, look at the sun and now move in the direction that's in the spread of 1/2 to that. Don't you need to know really whether you need to go northeast or southwest? One way there is salvation, the other way there is death and destruction.
Yeah, but so there's various conventions. That convention problem happens with angles too. I mean, is an angle of 12, this way or this way?
No, I agree, but it seems to me that sometimes, allowing yourself not to introduce negative qualities or orientations or something will actually improve things.
Well, maybe in one of my next talks, maybe next year, I'll tell you about vector trigonometry, which is a variant on rational trigonometry, which will make you very happy because the square roots are in fact incorporated, but the angles are not. So it's a kind of a halfway point between this pure rational trigonometry, which is 100% algebraic, and the usual trigonometry, which is highly transcendental.
Norman, your spread is sine squared theta, isn't it?
Exactly, yes. The spread is sine squared theta.
For the dihedral angle, you said it was different. Is it a function of...
No, the dihedral angle is just the sine squared of the angle between those faces.
And the solid angle, sorry, I meant the solid.
Okay, the solid angle has no direct relation to the solid spread.
To the 4 pi thing that we all know.
Yeah, that's right. They're not commensurable.
Okay.
It's a very interesting distinction. We're sort of going down different forks when it comes to those solid angles, solid spreads. Michael?
Well, do you have any sense of how it might generalize to, say, another platonic solid like an octahedron or something rather like that?
Yeah, I have some of the spreads in an octahedron. I mean, once you think of the tetrahedron as some kind of building block, one can analyze the octahedron using the same kinds of ideas, in the same way that one can study a pentagon once one has understood a triangle, roughly.
And a regular octahedron or a regular platonic solid?
Yeah, so we are in a position to understand those all metrically now. And there's quite interesting things that happen now. At some point I'll probably give a talk on the platonic solids. Yeah.
So there's the spread law for triangle, the spread law for tetrahedron. Do these indicate vaguely perhaps what the spread law might be for any simplex?
That's also a good question. Yeah, so there's certainly ideas suggested there, and I can't say that I've actually pinned that down completely. But I think this leads us to this issue of the geometry in higher dimensions is going to get more complicated. I think in a way that people don't quite understand yet. It gets a lot more complicated in higher dimensions.
So the formulas don't sort of shout out, it's just some...
Something like the spread law very well does go up, in a nice way. But some of the formulas, one can, like the cross law, I have no idea how that works out in higher dimensions. It's a good question, obviously.
Any further questions or comments? In that case, let's thank Norman once again.
Thanks.